Okay, this screencast will finish off our introduction to electric current by talking about the speed at which the electrons actually move around the circuit. It's not the speed that most people think. So the speed that they move around is actually called the drift speed. And so hopefully you get the idea that it's really not going to be very fast. We wouldn't use the word drift if it was really fast. And it's the average distance that a charge would move as it goes around the circuit during a period of time. Now, the drift speed is actually pretty slow for electrons because they're going to have to work their way through the material. And the material they're working through, even if it's a good conductor, is going to have a number of blocking atoms that don't want to let their electrons get away. So it is analogous or similar to trying to move or roll a ball down an incline uh, on which you have a bunch of blocks that are stuck in place. When the ball is rolling and starts to move, gravity will pull it down and make it start to move. When it encounters one of the blocks, it's going to have to change direction because it has to get past the block. So here our electron starts. It starts moving and bam, it runs into a blocking electron. So it has to change its direction. Now, in rolling down the hill, not only would the ball have to change its direction, it'll probably also come to a stop. Same thing will happen to the electron. So it'll speed up, it'll slow down when it hits the blocking electron, it'll change direction trying to find a new path through. Now, throughout this entire time period, the thing that's actually driving the electrons along is the electric field. Now, the electrons are negative, so they're going to move from negative to positive, so they're actually going to be moving against the electric field while they're in the wires. And every time they run into some other blocking electron, they're going to try to get around that because that field is going to force them to continually move to the right. And just like the ball rolling down the hill would constantly be trying, gravity would be pulling it down. So if there's nothing in its way, it's going to start rolling down and speeding up. So if you look at that path, it's quite convoluted. This is just an example path for the electron. Because the path has so many zigs and zags and so many different directions it has to take, it ends up moving a very large distance within the wire to move a length of the wire. And since speed is distance divided by time, all those extra zigs and zags mean that the typical drift speed can be as small as 1 meter per hour. Okay, so it's very, very, very slow. So it's not the electrons that move fast in the wire. That's a common misconception. So we turn on a light switch and bam, the light comes on. Now, I turn on a light switch at the front of the room and the light's all the way in the back. Those are like 40 feet away. They turn on. If it was the electrons at the switch that turned on the lights at the back, at 1 meter per hour, at 3 feet per hour, it's going to take over 10 hours for them to get there. And that obviously is not what's happening. So it's not that the electrons start at a given place and move around the circuit. Okay, that's not what happens. The battery doesn't supply the electrons, the light switch doesn't supply the electrons. What happens is it's like a very long train, many, many electrons all set up ready to start moving out. All they need is something to get them going in the same basic direction. Okay, so what does that is that electric field. So you flip the switch on, and within your wire, initially there are a whole bunch of electrons just waiting to go. Right? And that's all the way throughout the wire, through the light bulbs, through the switches, through all the different metals and pieces that we use to make up our circuit. When you switch on the circuit, it's not the electrons that have to flow all the way through the wire. You set up the electric field, okay, and then those electrons are going to be just like gravity would pull an object physically downward. The electrons are going to be pulled, and this is where it gets a little strange because of the way that Ben Franklin set it up with the idea that charge should flow from plus to minus. We're actually using the real facts that we now know, the charge flows from minus to plus. So that means those little electrons are going to flow against that field that I've drawn. So that means they're all going to start to move to the left. Now, they're going to drift, okay? But this electron is very close to the other end. So all it has to do is drift a little bit, and it can make the light bulb turn on. If the switch is way over here, it's not this electron that turns on the light bulb. It's the one that's over here right next to the light bulb. Okay. Now, the electric field signal, which is what tells every electron to get moving, it's like the gravity that starts pushing them or pulling them along, that sets up at the speed of light, or very close to the speed of light. Because of that, you can get a message all the way across the world in a very short period of time, because the speed of light is 186,000 miles per second. That's not meters per second, that's miles. That means light can wrap itself around the Earth about 7.5 times every second. So it doesn't take very long to start a message over here in the United States and have it come out 12,000 miles away on the other side of the world. A lot less than a second, that can happen. And again, it's not that the electron from here in the United States traveled across the world to the other side of the world. It's that the electrons over here in the electric field set up. The electric field was created throughout the circuit within at the speed of light. And then the electrons that were already on the other side of the world started drifting in the direction, in this case, against the direction of the electric field. So they're the ones that got the message to the other side of the world. Okay, so a quick wrap up on that. Which sentence best describes what happens to charge that moves through an electric circuit? It's not supplied by the battery or terminal. It's never created, okay? It's set in motion by the signal of the electric field. It's already there. It's just waiting to go. Everybody's lined up, and bam, the signal goes off and they start moving. How fast the charge moves. The charge does not move anywhere near the speed of light. It doesn't even move close to an airplane. It moves, and this is supposed to be C, it moves very, very slow. Slower than you could watch a snail move itself across the ground. And then 7, when you turn on the room lights, they light immediately. This is best explained by the fact none of the electrons are moving very fast. Okay. The electrons that are already present, and they're present everywhere in the circuit, as soon as the electric field hits, they start to move instantly. Now they start to move, but they don't move in random directions. If they did, then some would head toward the light, but some would come back this way, and some might go over this way. They all will move overall, as an average, in against the direction that the electric field sets up. So the ones that are already present everywhere in the circuit move instantly. All that's the same as part B, but now it's the same net direction, and therefore the electrons that are already close to the filament of the light bulb turn the light on and make it, they give up their energy as they go through it and make it turn on. Okay, now they don't all move in exactly the same direction. They drift. They might move in some kind of random pattern, but in general their overall direction will line up, and it will be actually against the direction of the electric field. Okay, so if you really understand how electrons move in a circuit, you'll have it'll be much easier to visualize what's going on later when we talk about more complex circuits.